Good morning, class. All right, today we're going to start talking about negative feedback. Up till now, we only talked about the open loop. That means we had an op amp without any feedback. All right. We look at the characteristics of the op amp, input impedance, output impedance, voltage gain. We looked at all those characteristics. But today we're going to start talking about negative feedback. What is negative feedback? When you want to do any control, you will normally make use of negative feedback. There's actually only one case. In our course, we're going to make use of positive feedback. That's when we can look at the oscillators. In the case of the oscillator circuits, there we make use of positive feedback. But here we're going to make use of negative feedback. And the purpose of that is to get basically linear operation with our op amp. Now, what do? We take from the output through a negative feedback circuit. That can be a resistor or anything like that. And we feed it back to my inverting input. Why to the inverting input? Because there's a 180 degrees phase shift between my output and my inverting input. If I go and look at my non-inverting input, there's not going to be any phase shift. Then it's not going to be negative feedback. You can see here, my input and my output is in phase. But what I'm going to feed back here is going to be 180 degrees out of phase. All right. That's why it's negative feedback. Any questions? Any questions? If we look at this, in this case, if I'm going to look at the op amp, open loop gain of that op amp, for example, 100,000. If I apply a 1 millivolt input signal to my non-inverting input, where will the output go? It will go positive because it's my non-inverting input. This input is my inverting input is my reference. I go positive there, it will go positive. All right. Now if we work it out, 1 millivolt multiplied by 100,000 should give me 100 volts. All right. You with me? Now, what will determine the maximum output of that device? What will determine the maximum output of the op amp? The input signal. What? The supply. The supply will determine the maximum. That means if I had a supply here of plus 15 minus 15, it will only go to plus 15. All right. Even it should go to 100 volts, but it can't go to 100 volts because the supply will determine the maximum. If I go and look at the input, according to this input, I should go to 100 volt output, but I won't reach 100 volt. It will be limited by the supply to the device. All right. In the next case, I apply negative voltage, minus 1 millivolt, also to my non-inverting input. That's why now it will go maximum negative. That is a device without any feedback. All right. All right, this table here just gives us an indication what happened when I apply negative feedback and what happens when there is no feedback. Now, first of all, they say without negative feedback. Then they say open loop gain, AL stands for open loop gain, is too high for linear amplifier applications. That means we think about a 741, it will be in the region of 200,000, all right. Input impedance, relative high. You will also find that on the data sheet. Output impedance, relative low. And they will also tell us a relative narrow bandwidth because the gain is so high. That means that is when I don't apply any feedback to the device. The moment I apply feedback to the device, then I can get a closed loop gain and I can get it to a desired value. That means I will determine what is the desired value depending on the ratio of my feedback resistors, right? They say it can be increased or reduced to a desired value depending on the type of circuit. Normally, my input impedance increased by a certain factor. If I look at the non-inverting amplifier, in the case of the inverting amplifier, it will be determined by the input resistor, but we'll also look at that a little bit later. The output impedance will be reduced. It will be reduced. That means it will come closer to the ideal value. We don't want a high output impedance, we want a low output impedance. And my bandwidth will also be increased when I apply negative feedback. All right. Now we're going to start looking at devices with negative feedback. We're going to look at the following. We're going to look at the non-inverting amplifier. We're going to look at the inverting amplifier. We're going to look at the voltage follower. Now I'm going to use a different sequence than the book. I'm going to start with the voltage follower. I'm going to do it quite practical so that you understand the operation. All right. And if there's any questions, you're welcome to ask. All right, in the books, that is on my book, that is on page 606. Figure 12.18, that's the voltage follower, all right. All right, here's the voltage follower. Let's have a look at the circuit. We take from the output to where? To my inverting input. Is that negative or positive feedback? That's negative feedback. From the output to my inverting input. That's negative feedback. My input is here at my non-inverting input. Now, we know an op-amp can work on DC. I'm going to put a DC supply voltage in there, or not a supply, a DC input voltage, just for explanation purposes, to help us, or help me to explain to you. I'm going to put in a DC supply of input voltage, DC input voltage. Let's say there's positive, there's negative. Let's make this input voltage 10 volts. All right. 10 volts in there. Now, there's a few things you must remember. The input stage of an op-amp is what? What is the input stage of an op-amp? It's a differential amplifier. All right. A differential amplifier. That means the op-amp will always try to make this voltage difference equal to what? When there's feedback. It will always try to make it 0. All right. Now, when I apply this, the output should be 0. But the instant I apply this plus 10 volts, what will the op-amp sense? Because there I got 0 volts, here I got plus 10 volts. What will the differential amplifier sense? It will sense an unbalance, all right. And it will do certain adjustments to rectify that unbalance. The op-amp will try to make this voltage difference equal to 0. You know what's 0? No voltage difference. Now, if I apply plus 10 here, to make this voltage difference, what should the voltage be? Speak up. Minus 10. Do you agree? Everybody? I don't agree. I don't agree. I didn't ask you to say plus 10 and minus 10, add them together. If I take plus 10 and minus 10 and I add them together, what do I get? Then I get 0. But if I look at the difference, I got plus 10, I got minus 10. What's the difference? It's 20. Now you're telling me 20 will give me a difference of 0. No. I say, what is the difference? The difference should be 0. Now, if I want a difference here of 0, what should the voltage be there? Positive 10. When I got positive 10 here and positive 10 there, what is the difference? 0. There's no difference. But if I got positive 10 and minus 10, what's the difference? 20. All right. Please remember, you S3 or S4 students, you tell me that. Eh? That means the op-amp will take its output here to plus 10 volt, feeding plus 10 volt back. There is no voltage difference. The whole story is in balance. Now you will say, sir, what is the use of a circuit? I put plus 10 volt in and I get plus 10 volt out. Or I put a sine wave in and I get a sine wave out. If I put a square wave in, I get a square wave out. What's the use of a circuit like that? What is the advantage of the circuit? First of all, what is a closed loop gain? The closed loop gain of that circuit. How do we calculate gain? How do we calculate gain? Can you help her? How do we calculate gain? Voltage gain. How do you calculate voltage gain? No. Just tell me, what do we use? How do we calculate voltage gain?
20 log of the ratio of the input over the output over the input.
All right, gain is the output voltage divided by input voltage. Current gain, output current divided by input current. All right. You can express it in dBs, but it's not necessary to express it in dBs, but it's the output divided by input. All right. Now, if I look at the gain here, the output is 10 volts, the input is 10 volts. What is the gain? 1. All right. That means the closed loop gain of that circuit is 1. Now, what is the use of a circuit like that? Well, I put in, I get out. Is there anybody that can help me? First of all, what can I say about the input impedance here? Very high. I got a very high input impedance. What can I say about the output impedance? Very low. That means I can use that circuit as a buffer stage. All right. I'm not going to draw any current from this source, and at the output I can draw current. All right. You with me? You can use the buffer stage. That is a voltage follower. Anybody, any questions? All right. Let's move on. Now the next one, what I'm going to do the inverting amplifier. The book starts with the non-inverting amplifier, then the voltage follower, then the inverting amplifier. What we're going to do next is the inverting amplifier. There's a circuit diagram of the inverting amplifier. All right. As it mentioned, it's going to invert the input signal. If I apply positive, the output should go negative. If I apply negative, the output should go positive. All right. Again, we're going to do it practical. I'm going to put in values, and we're going to do it quite practical. Again, with the DC source. Let's again apply here input plus 10 volt. Positive there, negative there. Let's make R in 10 kilo ohm. Let's make RF 10 kilo ohm. Now, there's a few things I'm going to tell you, what you should remember. Let's say without any input signal, the output should be 0. Now I apply this plus 10 volts there. All right. The instant I apply the plus 10 volts, we know that is at 0. What will the op-amp normally try to make the difference here? 0. If I got 0 there, what should be there? To make the difference 0. It should be 0. All right. But the instant I apply this 10 volts, yeah, that will tend to increase. Small increase. When my differential amplifier sends this increase, all right, it will tell the op-amp to go away, positive or negative. This goes a little bit up. Will the output go negative or positive of the op-amp? Due to the supply, the op-amp got a supply, will it go positive or negative? It should go negative, all right, because it's the inverting input. That means this output will tend to go negative, all right? It will go negative in such a direction to make sure this voltage difference is 0, all right? They normally call that point virtual earth. It's not directly connected to earth, but it will be the same potential as earth, all right? Now, if I assume that is at earth, what can I say about this current that's going to flow here? Can I calculate the current value? Yes, I got the voltage, because that's 0. I got the voltage as 10 volts here. I got the resistance there, R in is 10 kilo ohm. What can I say about I in? Because this point here is now going to be at 0 volts, all right? I will have a current flow that's going to flow in that direction, all right? I can say I in is equal to V in divided by R in. You agree? And V in this case is 10 volts, and R in is 10K, and that will give me 1 milliamp. You agree? All right. Now we know the input impedance of the device is very high. That means nothing is going to flow into the device. I can say there's 0 amps flowing there. All right. Now what does Kirchhoff's current law state to current flowing towards a node? All right. Or if there's only one node, it's equal to the current flowing away from that node. All right. That means there's 1 milliamp here flowing towards a node. That means nothing is flowing into the op amp. That means there should also be a current there of 1 milliamp. All right. Everybody with me? And to get a current flow in that direction, this point should be more positive than that point. That means the output should go negative. To what value? To create a current flow of 1 milliamp there. Because that's the other rule. Those currents must be equal. They must flow in the same direction and they must be equal. Not in the opposite direction, same direction, and they must be equal. Now what should the output voltage be to create a current there of 1 milliamp flowing in that direction? Anybody? Hey, wake up. It's still early in the day. Anybody in class? Positive or negative? What? Right. I got an answer. Let's write it in here. Plus 10. Now we look at that answer. Plus 10 volts. Which direction will the current flow? How does current flow? From positive to negative. Is it flowing in the right direction? Should be negative 10. It should be negative 10 because I use the inverting input. If it's positive 10, it will flow in the opposite direction. Wrong. That means the correct answer there should be minus 10 volts. All right. Then the current will flow in the right direction. What is the gain of that device? The gain is 1 because the output current is 10 and the input current is 10. It should be, they will tell you in the book, it's minus 1. The minus sign just indicates 180 degrees phase shift between the input and the output. All right. Do everyone understand? I repeat the rules. The op amp will always try to make this voltage difference 0. The input current and the feedback current must flow in the same directions. They must have the same magnitude. All right, if it's saturated, let's say I put a too high input voltage here and the device saturates, then we can't satisfy that. But if it's in the linear operation, then voltage difference 0, input current and feedback current, same magnitude, flowing in the same direction. You with me? Now we're going to change it a little bit. Let's make RF now a 20 kilo ohm. Same circuit, everything the same. The only difference, I change RF to 20 kilo ohms. All right. Again, op-amp tried to make the voltage difference 0. Don't worry about the supply. Let's say we've got a supply of plus 40, minus 40 volts. Don't worry about the supply. I don't give you a supply. If I don't give you a supply, it can be any value. All right. First of all, plus 10 volt, input current 1 milliamp. You agree? What should the feedback current be? Should be 1 milliamp. All right. Now, what should my output voltage be to create 1 milliamp to flow there? What should my output voltage be to create 1 milliamp to flow there? Huh? What? Positive or negative? Negative. It should be minus 20 volts. All right, let's go and have a look. Minus 20 volt, that means where does the output go? It goes negative 20 volts. Now if I look at 20 volts divided by 20k, it will give me what? 1 milliamp. That means the currents is correct. The currents are flowing in the correct direction. That means that is the correct answer. Is there anybody that can borrow me a ruler? No, I'm looking for not a short ruler, I'm looking for a long ruler. A normal length one. All right, there's one. If you look at this, when I got my ratios like the first one, a 10K and a 10K, I got a ratio of 1. That's like, if I look at the beam, and my pivot is right in the center. If my input goes positive, what happened to the output? Go negative with exactly the same amount. If my input goes negative, my output goes positive with the same amount. If I change this, if I make that resistor larger than my input resistor, I'm going to do that. If my input goes positive, the output goes negative with a much larger amount, depending on where I move it, all right? If I go negative at the input, the output will go positive with a much larger amount, all right? That is, I just basically change my attenuation, all right? Any questions? Let's quickly have a look at the proof. We actually basically did the proof already. If you look at the case of the voltage follower, there they show us the voltage follower. They say the closed loop gain of a voltage follower is equal to 1. All right. And now we can look at the inverting amplifier. There's the inverting amplifier. First of all, they state there that I-in is equal to IF. I already mentioned to you the input current and the feedback current is equal. The input current is equal to the input voltage divided by R in. We did that. And if we look at this, there they show us virtual ground. It's not connected directly to ground, but that's virtual ground. All right. And there they show us I in and IF. And there they show us no currents flowing into the device because we've got a very high input impedance. We go a little bit further. There we can say that IF is equal to minus VR divided by RF. And we can say those two, we can set IF and IN equal to one another. Minus VR divided by RF is equal to VN divided by RIN. And we want the voltage gain. How do you determine voltage gain? It's the output voltage divided by the input voltage. That's why I can say V out over V in is equal to minus RF over R in. I repeat, minus sign indicates 180 degrees phase shift between the input and the output. There they say the closed loop gain of an inverting amplifier is equal to minus RF divided by R in. Let's have a look at the example. Example 12.4, they say given the op-amp configuration in figure 12.21, determine the value of RF required to produce a closed loop voltage gain of minus 100. I repeat, minus 100 just indicate 180 degrees phase shift. The input resistance is equal to 2,2 kilo ohms. We must calculate RF. We know the gain is equal to 100. That's why I can say RF is the absolute value of the closed loop gain. We don't need a negative there. We want to calculate the resistor. It's 100 times 2,2 kilo ohms will give me 220 kilo ohms. That means with 220 kilo ohms, I will have a gain of 100. All right. The device gain can be 200,000, but now when I apply the feedback, I can get 100 or what the case may be. Any questions? Now we're going to look at the non-inverting amplifier. That means in this case, my input and my output is going to be in phase. We're again going to do it very practical. Right, here's my non-inverting amplifier. You can see where's my input. My input is at my non-inverting input. That means my input and my output is going to be in phase, all right? Here we got a feedback circuit. What is that? Known to you. Voltage divider, all right. That means part of the output voltage, certain amount of the output voltage, the voltage drop across R1 is going to be feedback, all right, to the inverting input. That's why it is not a negative feedback. The output will go positive and I will feed back a part of that to my inverting input, and here I will get 180 degrees phase shift. All right. Again, now we're going to do it practical with DC input voltage. All right, let's say positive there, negative there. Let's make it 10 volts again. Let's make again RF 10 kilo ohms, R in 10 kilo ohms. And let's go and work through the circuit. What's going to happen? Again, output is 0. I apply plus 10 volt at my non-inverting input. What will the op amp do here? What will it try to make this difference again? 0. All right. Again, try to make it 0. That means what must I feed back here to make the difference 0? What must we feed back? What must we feed back? Repeat. We must feed back positive 10. I got 10 volts there, I must feed back positive 10, all right. But now we must go and have a look, what should the output be to feed back positive 10? That means the volt drop across R in should be 10 volts. You with me? And now I'm feeding back 10 volts there. That means what must the output be to feed 10 volt back? The output should be 20. 100% correct. 10 volts across there, 10 volts across there, because these two resistors got the same value. If I got 20 plus 20 at the output, I will have plus 10. I'm feeding back plus 10. The voltage difference is 0, and the whole story is in balance. All right. What actually will happen, the output here will be plus 20 volts. That means it will be positive, negative, negative. 10 volts across there and 10 volts across there. All right. As simple as that. Now what I'm going to do, if we look at this, what is the gain of this circuit? The gain is 2. With those resistors, my gain is 2. The output is 20 volts, the input is 10 volts. If we're going to work it out, the gain is 2. All right. Now is there any questions there? Everybody with me? Everybody happy? All right, let's go and look at the proof of this non-inverting amplifier. That is on page 604 of my book. It's a proof of the non-inverting amplifier. We're going to quickly work through the proof of the non-inverting amplifier. All right, first of all, when you look at this, I can say VF, my feedback voltage, is equal to Rin over Rin plus Rf times V out. V out is a total voltage. Part of that, the volt across Rin is going to be feedback, and that will be my feedback voltage. That's a normal voltage divider, all right. Right, they say, now they're going to look, they say the difference of the input voltage Vin and the feedback voltage Vf is the differential input to the op-amp as shown in figure 16.2. The differential voltage is amplified by the open loop gain of the op-amp. Please remember, AOL stands for the open loop gain and produce the output voltage expressed as. They say V out is the open loop gain times my differential voltage. What is my differential voltage? It's the input voltage minus my feedback voltage. All right. And then they talk about B, the attenuation. The attenuation of the circuit is Rin over Rin plus Rf. That is the amount with which we are going to attenuate the output signal. All right. That is my attenuation. We will work a lot with this B always as my attenuation. But we also know, if I take my attenuation times my output, that will give me my feedback voltage. All right. That will go to my inverting input. There's my feedback voltage. And then we can say V out is equal to open loop gain times V in minus my attenuation times my output. We can multiply right through by my open loop voltage, and I can say V out is open loop voltage times V in minus the open loop voltage times my attenuation times V out. If I take that term across the equal sign, it becomes positive. Then I can say V out plus the open loop voltage times my attenuation times V out is equal to the open loop voltage times V in. What do we take out? It's a common factor, V out. 1 plus the open voltage times my attenuation is equal to the open voltage times V in. What do we want at the end of the day? What do we actually want to prove? We want to determine the voltage gain. And how do I determine voltage gain? I determine by output divided by input. All right, you with me? And that is why I want, in my equations, I want my output and I want my input. At the end of the day, if I can say V out divided by V in will give me my voltage gain. All right. All right, there they say, since the overall voltage gain of an amplifier in figure 12.15 is V out over V in, it can be expressed as, all right? V out over V in, that is my voltage gain. It's equal to open loop gain divided by 1 plus the open loop gain times my attenuation. Now they state, the product of the open loop gain times my attenuation is typically much greater than 1. So the equation simplifies to, I can say V out over V in, open loop gain over open loop gain times my attenuation, and that is equal to 1 upon my attenuation, all right? And we know the attenuation is what? Rin over Rin plus Rf. It's a closed loop gain of a non-inverting amplifier is a reciprocal of the attenuation B of the feedback circuit voltage divider. Closed loop gain V out over V in is 1 upon my attenuation is Rin over Rin plus Rf over Rin. The Rin cancels out, then I can say the closed loop gain of a non-inverting amplifier is equal to 1 plus Rf over Rin. If you can remember about our example, we had two 10Ks, all right? That means that will give us 1 plus 1 is equal to 2. That means this circuit will always have a gain greater than 1, all right, or larger than 1. Always have a gain larger than 1. Any questions? Let's have a look at the example. The example states, determine the closed loop voltage gain of an amplifier in figure 12.17. All right. They give us RF 100K, Rin is equal to 4,7 kilo ohm. And we use the formula. It's 1 plus 100K divided by 4,7 kilo ohm, and it will give me 22.3. All right. But as I mentioned, gain will always be larger than 1. Any questions? Any questions? All right, we did the voltage follower. We did the inverting amplifier. The next part of the work is going to be 12.5. Effects of negative feedback on op-amp impedances. I think next class we will start with that. I want you to go through this part of the work, and then we'll start doing effects of negative feedback on op-amp impedances. All right. Any questions of the work? Any questions?